Hi, I am Dr. Samir bin Osman, and in this video we're going to talk about the principles of engineering sciences. I'm going to split this video into two sections. The first is just the general principles and the behavioral materials and how we use them in engineering. And the second is going to be about giving examples of some engineering specialties and how basically they think and how they operate, like in electrical engineering, chemical engineering, etc. So let's talk about kind of the general principles of engineering. So contrary to foundational sciences, which give tools for understanding our environment, engineering uses these tools to solve problems that are related to human living, human comfort, and human operation. So most engineering sciences work with two fundamental physical forces, which are gravity and the electromagnetic force, and the remaining nuclear forces are utilized in nuclear engineering. So gravity is going to dictate the weight of objects relative to their masses, and it's going to intervene by pulling them towards Earth and other celestial objects. The electromagnetic force is going to dictate five basically characteristics. First is the strength of the electronic bonds between atoms and molecules. That's going to give the properties of materials, the mechanical properties in rigidity, flexibility, etc. The electromagnetic force also dictates the heat transfer, which is the vibration and collision of atoms and molecules, which repel each other like kind of the same poles of two magnets, like we spoke about in chemistry, which is the base of heat transfer and heat properties. Then it gives magnetic properties to electrons that add up and form either magnetic materials or non-magnetic. And we're going to talk about each one of those in a little bit more detail in the next slides, but I just want to give you kind of the lay of the land here. The electromagnetic force also is going to dictate the movement of free electrons that jump from atom to atom, and which generate what we call the current, electrical current, which is the base of electricity. And that's going to also dictate the movement of photons in form of electromagnetic waves, which going to determine their behavior and usefulness in the transmission of images in optics or data encoded in telecommunications, or to transfer concentrated energy to other atoms like microwaves using ovens, etc. And then we have, like we said, the nuclear forces that are used in nuclear physics or nuclear engineering. And we have the strong force that's going to dictate how large atoms going to split into smaller atoms, and the small ones, how they're going to fuse into larger ones to release some of the strong force as heat, which is used for electricity generation, nuclear plants. And the weak force is going to dictate the radioactive decay rates of unstable atoms, which are used in medical imaging or at higher energies for radiation therapy. So let's talk about the properties of material, take them one at a time, and understand the principles that govern how they behave and how they can be leveraged in engineering. So the structure and behavior of materials are dictated by the types of atoms and molecules that compose them. This is kind of the general overarching principles. And that's why you need to choose carefully what atoms you want to put into your material, into the alloy or product that you want to design. And so that's going to give them the properties that we're going to talk about. Now, what I want to highlight is that all the properties are going to happen at the same time. Remember the second principle that I said, like everything happens at the same time and everything is interlinked. So every material is going to have mechanical properties, heat properties, magnetic properties, optical properties, etc., etc., etc. And so depending on the application, the engineering application, some of the properties will be very relevant and very important to focus on, where others may not be relevant to the application that we're talking about. So for example, I don't know, like, if you were designing optical lenses, the optical properties are very important for the material we choose, but the electrical properties not so much. And so with that in mind, let's talk about the mechanical properties of materials. So solid materials are made up of different atoms that are held together by intermolecular bonds, like we explained in the chemistry video. Those intermolecular bonds will cause them to arrange themselves in configurations that minimize their energy. And so when we have like solids that are like packed, densely packed together, they will form what we call crystals, as you can see here. And they will be basically perfect arrangements. Or they can have cracks and defects or flaws, as you can see here in this electron microscopy of a metal, where you can see kind of zones where you have like perfect arrangements, and between those zones you have flaws. These are atoms, by the way, like the dots that you see here are atoms. And so all materials, they will be subjected to forces that we call stresses, which depending on the region or the direction that they come from can be either compressive, as you can see here, like pushing each other, tensile, which is the opposite, shear, which is like from one side to another, bending, twisting, etc. So what is the effect of those stresses on the distribution of atoms in those materials? So the stresses, they will change the distance between atoms. And at first, if we apply a small stress, they will change the distance between atoms without changing their arrangement at the beginning, i.e. just like a rubber band. Imagine a rubber band, but like with atoms. So you just stretch them and they come back, stretch them, you come back. So you're basically just changing the distance between the atoms in a non-destructive way. And that is called elastic deformation. Now, as soon as the stress is removed, those atoms will remove to their initial arrangement just like nothing happened. So that's kind of the elastic deformation. However, beyond a given threshold of stress, the stress that causes the arrangement will cause them to dislocate at the location of the defects or the flaws that we saw. So basically they will slide against each other. Just like geological tectonic plates, they slide against each other. So you can see the same thing at like a atomic scale, where these kind of zones will slide against each other. And so the fact that they slide is irreversible. They cannot come back the way they were. And that's why they call it plastic deformation. So like you take a piece of metal, you bend it to a certain point, it will stay as is. It will not come back to its original shape. That's because there was irreversible sliding of atoms along those defects, along those faults. Beyond the second threshold of stress, the stress is going to cause the molecular bonds to break. And basically, it's going to cause the material to rupture. So that's what we call failure in mechanical properties. Now, some materials do not have perfect elastic deformation. And so with repeated stresses, so you apply the stress and then you stop, and you apply and you stop. And every time you apply, they will gradually exhibit a small plastic deformation. And that small plastic deformation is going to grow and grow and grow. And that's what's called fatigue. And that's actually a precursor to rupture, to failure. And so in the example that you see below here in the plane, these are like old designs for the windows for the planes. And the old designs were square. And they didn't realize that every time the plane goes in the air and it gets pressurized from the inside so that we can keep ambient pressure, the pressure applied from the inside on the plane is going to cause stress on the entire structure of the plane, which for the most part was fine, except that at the angles, it applied a lot of stress. And then every time the plane lands and it depressurized, the stress stopped. And so the stress on and off and on and off every time the plane flies caused fatigue and many cracks in the kind of angles of the windows. And actually, ultimately, it caused many of them to explode in midair, and actually the entire planes went down because of that. And so they learned from the mistakes, and now you see in the planes, all the windows are round. They don't have like places for prone to high fatigue. So then the atomic composition, how do we know like how these materials will behave? So what's important here, the principle that I want to come to is here, the atomic composition and the manufacturing method of the material, i.e. heating, the way it was heated, the way it was cooled, the stresses that were applied on it during its heating or cooling, the chemical reactions that were applied to it while it was formed, all of these will determine the elastic and plastic threshold, i.e. some materials will have very little elastic threshold and then they will become plastic. So like very little kind of give, and then they will start to bend. Some others, no, they will not bend, and then they will break, just like glass, for example, And so these thresholds will be used to make strong materials for constructions, for example, and structures, or flexible ones for joints, etc. So that it's very important to know what are the thresholds to determine what materials do you need to choose, or the material do you need to develop to gain those thresholds for the application that you're looking for. All of what I said only applies to solids, by the way. So then in fluid materials, the atoms are held together more loosely, so they don't form like those crystal arrangements, which means that all stresses will cause plastic deformation. Like every time you put your finger on a liquid, you're deforming it, and it's not gonna come back the way it was. And even if it comes back, it's not gonna be the same atoms. It's gonna be rearranged anyway. So the speed at which the deformation is caused determines what we call its viscosity, i.e., for example, when you deform a liquid like water, and when you deform a liquid like honey, they will not move at the same pace, because honey is much more viscous than water, which means that it resists this deformation a lot. And so the liquids, they will have this property of viscosity. That also is very important when we try to make components that are made of fluids, just like lubricants in engines and things like that. Determining the ideal viscosity is important, and that's going to determine what material you choose or material you develop that has the right viscosity. So that's it about mechanical properties. Let's talk about thermal properties. So heat, like we said, propagates directly when atoms collide or transmit their vibration through their intermolecular bonds, which happens in solids and fluid materials. Especially in the gases, they don't have like those intermolecular bonds, but they propagate their heat when they bump into each other. And so the molecular density and the number and the strength of intermolecular bonds, these will determine how much heat this material is going to store, which is called thermal mass, and then how quickly it's going to transfer it between itself or to another material, which is called thermal conductivity. And so these properties are carefully chosen to design thermal insulators, for example, in construction or like in spacecrafts, as you can see the ceramics that they put on the bottom of the space shuttle. Or on the opposite, thermal conductors like cooking utensils, and you can see here, for example, copper-made cooking utensils, which are like a very good conductor of heat. So this is kind of the principles of thermal properties of materials and how they're chosen. Now let's talk about chemical properties. So the molecules that make up a material can have a polarity or be nonpolar, and we spoke about this quite at length in the video about chemistry. So if you need more detail, I will send you to the video about chemistry. So this polarity or non-polarity is going to dictate the material's ability to either bind or dissolve in, or non-bind or repel or non-dissolve in polar water molecules or non-polar molecules. So if it binds into water molecules, it's going to be called hydrophilic. Hydro means water, philic means loves. And if it doesn't like water, it's going to be called hydrophobic. Hydro means water, phobia means like to repel or not to like. And so you can see here, for example, in this image, in the above, you can see a leaf, which is actually naturally hydrophobic. And you can see the water droplet does not kind of embrace the water, the leaf, and it just like stays above it. And we can use this property to engineer actually products that are hydrophobic or like super hydrophobic, like this clothing pieces on the right that have been treated by a nanomaterial that makes them super hydrophobic. And you can see when you throw the mud on the person on the right, there is very little, if any, of the mud that's going to stick, because mud is hydrophilic, and the shirt and the tie, etc., are super hydrophobic. Whereas the guy in the left is enjoying being soaked in the mud bath. Now, there's another property, chemical property, which is the reactivity of materials. So materials with an excess or a lack of electrons will seek to react with other molecules, and therefore they're called reactive. While other materials with balanced number of electrons, i.e. not too many, not too like insufficient number of electrons in their valence, will be poorly reactive. And you can see here like the reactivity scale from gold, which is not reactive or less prone to reactive, to potassium, which is like highly reactive, and sodium. Then these properties will be studied and carefully kind of determined to find or design chemical reactions that make products that we of interest that we want to make, such as, for example, the production of soap through the chemical reaction of saponification, or to prevent unwanted reactions such as the oxidation of corrosive metals, which you can see here in the picture. That's going to gradually eat into them and cause them to fail. So this is kind of an overview of the chemical properties. Now let's talk about acoustic properties, so sound properties. So what is sound? So sound is a pressure wave that propagates through atoms and molecules that basically hit the adjacent atoms, which in turn hit the adjacent atoms, etc. It's like a pressure wave, as you can see here in the image above, the pressure wave of like those atoms. You can think of them as those little dots. And obviously that's why sound does not propagate in vacuum of space, because there is nothing to bump against each other. And so that's why you don't hear you don't hear an astronaut screaming in space. The pressure that they create is going to create a wave, and you can see in below, if we kind of represent this pressure, it's going to be a wave, and that wave will travel more or less depending on the type of material. So what's going to dictate whether it's going to travel or not? So the principle here is that the denser the material, the more atoms there are, and the less the wave is going to travel, because there's more atoms that you need to bump into in order to move anything. And so those materials will be acoustic insulators, as you can see here above. And conversely, the less dense the material is, the more it acts as an acoustic transmitter, because the wave is going to move more freely, which is basically evidenced by the air that's above the speaker here. And so as you move the membrane of the speaker is going to create those pressure waves that you see on the right hand side, and those pressure waves will spread much more easily in the air than they spread in an acoustic insulator. So this is kind of a little bit of overview on acoustic materials. So let's talk about magnetic properties. So depending on the number of electrons in an atom, some electrons will be arranged in pairs, and when they are arranged in pairs, they always have magnetic fields that are opposite. And like we said before, the electrons are basically just like teeny tiny magnets, and so they have a positive and a negative in and of themselves. This is kind of an inherent property of the electromagnetic force. And so when you have those paired electrons, they will cancel each other out, because they will have always opposite polarity. And we said the electromagnetic force is a unidirectional force, as opposite to the gravity, which is not. It's a multidirectional force. And so the paired electrons cancel each other out, but there are always unpaired electrons, i.e. like single electrons. And those single electrons, they will have a charge, and they will have a magnetic pole and orientation. So the number of unpaired electrons, this is the principle here, the number of unpaired electrons in the atom that make up the material will dictate whether this material will have magnetic properties or not. But that's not the only thing. So the alignment of all these unpaired electrons will determine whether they will cancel each other out between the atoms or not. And so the unpaired electrons that are kind of in all different directions, they will cancel each other out. Everyone will cancel somewhere else. And so you have non-magnetic materials. However, the unpaired electrons that are aligned, they will construct magnets. And obviously materials that where the polarity can be changed, like some metals, they will be able to align when you expose them to a magnet, and so they will be attracted by magnets, and that's what we call paramagnetic materials. And so you have paramagnetic materials, magnets, and non-magnetic, or they called also diamagnetic materials. So these properties are also studied carefully when you want to exploit the magnetic properties of materials to design the product that you're engineering. Now let's talk about electrical properties, which is kind of the other side of magnetic properties. So what is electrical conductivity first? So electrical conductivity is the ability of materials to have what we call free electrons in their valence shell that can move, that can flow. And the flow is called the electrical current because it's a flow of energy. Now, the fewer electrons, the less conductive the materials will be, and so they will be called insulators. And the more dense the material is, the more the electrons will be able to jump between atoms, and though they will have more potential for conductivity. However, conductivity doesn't happen unless you have to submit it to a magnetic current. So for example, here you see a conductor with no magnetic movement, and so the electrons are freely jumping between atoms, but they're jumping in all different directions, and as such they will also cancel each other out, and so there is no electrical current. However, when you expose that same conductor material to a strong magnetic force, let's say like a big magnet or something like that, that's going to force all these free electrons to align in the same direction and follow the magnet in which they are, and so they will flow, generating thereby an electric current. And so the ability of the electrical conductivity will be determined by, again, the molecular composition, the density, and the arrangement of the components of the material to be like more or less conductive. Now, one thing that I want to attract your attention to, now we're talking about conductivity, is that there is no such thing as a perfect insulator. So like every material will offer, like no material will offer like infinite resistance to the flow of free electrons. And so there's always a threshold of power above which electricity will flow through an insulator. Now, on the other hand, if we take it all to the other spectrum, there's always some resistance to the movement of electrons. They will not move like with like perfect efficiency. There will always be like some that will bump into each other, etc. So that's called resistance, and resistance generates heat, because we said heat is kinetic energy, and electrons will bump into other electrons or into the atoms, and so they will lose some of that energy into heat. So resistance is always generating heat. However, there is a special type of materials that offer no resistance to the flow of electrons, and they're called superconductors. And those superconductors are basically super efficient conductors of electricity. The problem that we have with superconductors now is that they're only able to operate as superconductors in very low temperatures, like minus 196 degrees Celsius or something like that. But there are efforts to produce what they call high temperature superconductors. High temperature is like a euphemism. They're trying to produce room temperature superconductors. That's what they call high temperature. And if they manage to produce them at like an industrial scale, it could revolutionize electrical engineering applications as we know them. So let's talk then about optical properties now. So depending on the atomic structure of materials, the electromagnetic waves of light, i.e. photons, will have either enough energy to move the electrons, which actually will absorb them, or just enough energy to make them vibrate. And then the electrons will combine with them to form a new slower electromagnetic wave. So they will emit another photon, but with a slower electromagnetic wave. And that's actually what explains why light is slower in transparent materials than it is in vacuum. So if light is absorbed, the material is actually opaque. And the light, when it's absorbed, is going to be converted into kinetic energy. Kinetic energy is what? Is heat. That's right. And so if the light is transmitted through the material is called either completely transparent or translucent, which is partially transparent. And transparent materials, they will differ in their properties of slowing down the light. Those like slowing down, they will not have the same capacity to slow down the light waves or the photons, and therefore to bend them. And that property is called refraction. And also they will not have the same ability to separate different wavelengths from each other. And that's called dispersion. And you can see here, for example, the dispersion on the right and diffraction on the, dispersion on the left and diffraction on the right. So let's talk about radiological properties or atomic properties. So atoms, they exist in nature in various isotopes, like we said, which have different number of neutrons, more than the protons in their nuclei. And so they're less stable, and they want to lose those neutrons. And when they lose them via the weak force, they will emit radiation, beta radiation, to stabilize themselves. And so the materials that include or that contain radioactive isotopes will differ in the energy that they will emit, the radiation that they will emit, which will define the wavelength at which they will emit them, i.e. the energy of penetration that they will have. And so some of them will penetrate into biological tissue, some will penetrate into metal, some will penetrate into concrete, as you can see here. And the higher energy, the more they will penetrate. And so this property is used to do medical imaging, for example, by using X-rays that go through the human body and that can be reflected in a sensor, or to leverage radiation that becomes heat in nuclear power plants that articulate steam, that heat steam, and steam generates the movement of a steam turbine, which in itself generates electricity via a generator. And so there's also another application of radiological properties of materials, which is dating in geology, which is basically using the ratio of disintegration of the radioisotopes of carbon to determine how much time the particular object lived, and so determine its age. The last property that I want to speak about, that's not kind of a physical property, but let's call it an emergent property, which is cost. And it's a very important one. So the cost of mining the raw material, refining the raw material, the raw ore, and transforming the material into the product that you want, the object that you want to use in engineering is very critical, because in engineering, we're not just kind of concerned about producing a device or like a solution to a problem, but also doing it in a cost-effective way. And so cost is the last material property that engineers pay close attention to. Now that we talked about how kind of materials behave, how materials, what properties they have, how do they behave in movement, or like the under stresses? So let's talk about material behavior in static objects, for example, to begin with. Engineers, they combine materials in well-calculated shapes to form what we call structures. And those structures are designed to hold up against the stresses that are applied to them that we've talked about, the compression, torsion, etc. Those static objects are always under stresses ranging from gravity, which creates what we call a load on the surface by pulling it down, or other stresses that we call variable stresses, just like wind, earthquakes, water, etc. And those structures will range from like building structures to car structures to even biomedical implants that are artificial joints and artificial hips that need to withstand the loads from a human body's weight, or furniture, appliances, electronics, robots, like you can hear like a robot arm, etc. So it's very important to understand the loads to determine what materials and what structure to design. The second is like their behavior in moving, or like dynamically. So the loads that we talked about in static objects, they will actually in principle apply the same way to moving objects. However, they will be different in the magnitude or the direction, given the speed and the medium in which those objects will have to move. So when two solid objects interact in a mechanical process, such as cogs or wheels or anything like that, the forces will be applied at the point of contact, and so it's important to calculate them at the point of contact. However, movement within fluids will displace the molecules of all the fluid that surrounds the object in order to accommodate the volume of that object. And so this displacement causes the medium of the molecules to quote-unquote rub against the molecules of the product, which is called friction, which will absorb some of the motion energy and convert it into, you guessed it, kinetic energy, i.e. heat. And so the volume and the shape of the product respectively will dictate how much of the medium it displaces and how quote-unquote abruptly it does so in what is called aerodynamics, when the object is moving in the air, or hydrodynamics, when the object is moving into fluids. So I want to kind of conclude this section by talking about some important engineering design principles. Not all of them, it's not going to be a comprehensive list, but some of them. So the engineers, they have to design robust systems that are going to resist either failure or human error by implementing some of these principles, one of which is redundancy. So what is redundancy? It's basically the duplication of critical components or critical functions. So if one of them fails, the object or like the product still performs its function. It's able to kind of perform it via the duplicated one. And you can see here in the example, we have an airplane cockpit, and you can see on the right hand side, it's basically a copy of everything on every button and every screen that exists on the left hand side, and that's called redundancy. So in case one side of the cockpit is non-functional, the other side can still fly the plane, or if one pilot is incapacitated, the other pilot or co-pilot can still pilot the plane. So this is an important design principle. The second design principle is designing with what we call margins of safety, or safety margins. So what does that mean? It's the ability to withstand more than the expected working loads and stresses. And it can range from 120% of the expected stresses to all the way to 400% of the stresses, depending on the application. And you can see here in this illustrated videos, to just stay in the kind of aerospace example, they're testing here the ability of an airplane wing to withstand vertical stresses. So they're like pulling it all the way up and pulling it all the way down to see how much it can withstand. But just they will calculate that it needs to withstand X amount of force, but they will always design it with more than the force that is needed. They will design it to withstand 120% or 200% of the force that will be under. Why? Because you never know. Things happen in nature, things happen that kind of may expose them to more than what they're capable of. So always design with margins of safety. The other principle is error preventing interfaces. So what does that mean? Is that basically you need to design an interface, be it like a physical interface, like you see here in like the airplane cockpit again, or like a computer interface, web interface, etc. You need to design them in a logical, clear way. That's basically that follows a logical order. You know, if you have a process that starts with A, B, and C, and D, you put like the buttons for A next to the buttons with B, next to the buttons with C, etc. But also you want to avoid accidental operation. And you can see here, for example, the first thing that's going to jump at you in this image is the red buttons. And you can see the red buttons 1, 2, 3, 4, 5. They're done that way because you can quickly identify them and you know it's red. So like you're not supposed to push them unless you know exactly what you're doing. You cannot push them by mistake. And even if you try to push them by mistake, as you can see, those buttons are covered. So you cannot actually physically push them. You have to open the lid before pushing them. So that's called error preventing interfaces. The last design principle I want to talk about is early warnings. And so which is basically the control of parameters that are critical, and then designing alerts that go off in the event of those kind of parameters going beyond the normal values, what we call nominal values. And you can see here, for example, you have an altitude alert light that switches on if the altitude of the plane is not high enough vis-a-vis its speed to be able to safely fly. So these are kind of some of the design principles. They're not all of them, but it gives you an idea of how the engineering mind thinks. And with that, we're going to conclude this video on the first part of engineering. In the next one, we're going to talk about some examples of how specific specialties in engineering think. And I welcome your comments and thank you for your attention.